Legacy systems, modern survivability, transforming existing platforms with nano-engineered stealth polymer, ML by Malcolm Lamont. This document explores how Queensland Research Labs' breakthrough nano-engineered stealth polymer technology can transform legacy military platforms into viable assets for 21st century electromagnetic battlefields without requiring structural modifications, thermal disruption, or active countermeasures. We present a cost-effective, logistically simple solution to extend the operational relevance of existing defense systems against modern multispectral threats. The modern battlefield presents a complex electromagnetic environment where legacy platforms designed in analog eras face sophisticated digital detection systems. Thousands of aging military assets worldwide, from Cold War-era destroyers to fourth-generation aircraft and mechanized ground vehicles, remain in active service despite their increasing vulnerability to advanced sensors. Traditional approaches to modernizing these platforms have required invasive structural modifications, including radar-absorbing cladding, thermal suppressors, and active jamming suites. These solutions are not only prohibitively expensive, but also time-consuming to implement and logistically complex, often requiring platforms to be removed from service for extended periods. High radar cross-section or RCS signatures, susceptibility to high-resolution LiDAR, vulnerability to optical tracking systems, detection by laser-based targeting systems. When we look at traditional upgrade methods, there are some significant constraints. We're talking about prohibitive costs, extended service interruptions, weight penalties that can really affect performance, and not to mention aerodynamic compromises. Our proprietary stealth polymer, it really represents a quantum leap in materials science. It's engineered at the nanoscale to interact with and absorb electromagnetic radiation across multiple frequency bands. Unlike traditional radar-absorbing materials, which usually target only narrow frequency ranges, our polymer's molecular structure actually creates a passive absorption matrix that's effective against a wide array of detection technologies. This is made possible by an extensive molecular lattice, which features adaptable response characteristics across the entire electromagnetic spectrum. Our advanced solution is simultaneously effective against X-band radar, millimeter wave systems, infrared sensors, and also optical and laser targeting systems. The customizable formulations allow us to address specific threat profiles while still maintaining thermal neutrality and structural integrity. The truly revolutionary aspect of our polymer solution lies not only in its electromagnetic properties, but also in its remarkably straightforward deployment methodology. It's engineered for seamless integration with existing maintenance cycles, and our coating can be applied using standard equipment and techniques that are already familiar to military maintenance crews worldwide. Standard degreasing and surface cleaning using existing protocols, which usually takes about 24 to 48 hours. Conventional spray equipment delivers a coating that's about 1 to 3 microns thick, and this process typically takes 12 to 36 hours, depending on the size of the platform. After application, we proceed with ambient temperature curing, followed by electromagnetic verification testing, a process that generally spans 24 to 72 hours. No additional modifications or systems integration are required. This means immediate deployment is possible. The total application timeline is just 3 to 7 days, compared to the usual 6 to 18 months needed for traditional stealth modifications. Plus, the ultra-thin nature of the coating, just 1 to 3 microns, ensures there's absolutely no measurable impact on weight, aerodynamics, or the structural integrity of the platform. Our nano-engineered polymer delivers unprecedented electromagnetic protection while still maintaining the critical performance parameters of the host platform. Unlike traditional stealth technologies, which often compromise operational capabilities, our solution actually enhances survivability without any negative trade-offs. Radar. Broadband electromagnetic absorption is achieved through impedance matching and internal scattering, which reduces the radar cross-section across X, Q, and S bands. For LiDAR, quantum bandgap resonance and Van Hove singularity-based absorption work together to absorb and suppress high-resolution LiDAR pulses. When it comes to laser-based tracking, photon energy is neutralized via quantum confinement and pi electron coupling, leading to a minimized reflective signature and degraded beam return. In terms of optical detection, optical bandgap tuning and volumetric scattering provide visual signal damping, reducing visibility to optical sensors. For thermal imaging, heat flux dispersion is managed through extreme internal surface area and phonon coupling, which lowers the thermal signature and eliminates hotspots. Finally, against directed energy weapons, energy-to-heat conversion and dispersion occur through nanoscale conductive pathways, allowing for high energy absorption and really minimal structural damage. Our polymer technology actively neutralizes multiple detection threats all at once, providing comprehensive protection across the electromagnetic spectrum in combat environments. We're ensuring operational effectiveness while maintaining all the critical platform capabilities. So, speed, maneuverability, and payload capacity remain completely uncompromised, while survivability, well, that dramatically increases. With this, we can transform vulnerable legacy assets into survivable platforms that are capable of operating in contested electromagnetic environments, effectively increasing the operational fleet size without the need for any new acquisitions. This low-profile format really makes it ideal for rapid integration over existing coatings, without impacting the platform's geometry, aerodynamic profile, or infrared signature. Platforms that were previously considered for decommissioning due to electromagnetic vulnerability can actually remain in service for like 10 to 15 additional years, which really helps defer those massive capital expenditures. Minimal downtime for application, about 3 to 7 days, means force readiness is maintained, and this can be integrated into scheduled maintenance cycles without disrupting operational tempo. By applying this material, platforms designed way back in analog eras can now absorb and nullify threats from digital era sensors. They re-enter the strategic equation, not as vulnerable liabilities, but as survivable, multi-theater assets that are totally capable of countering advanced detection and targeting networks. So, we're talking about fourth-generation fighters like the F-16 and F/A-18, transport aircraft such as the C-130 and C-17, and helicopter fleets including the UH-60 and AH-64. Destroyers and frigates, amphibious assault vessels, and then patrol craft and coastal defense. All of these platforms stand to benefit from our advanced materials. Main battle tanks, armored personnel carriers, and of course mobile artillery systems are all included in our approach. The versatility of our polymer makes it suitable for virtually any military platform requiring enhanced survivability against modern electromagnetic detection systems. Plus, application protocols can be adapted to the specific maintenance facilities and capabilities of each service branch, requiring minimal specialized training or equipment. At the moment, we're at current TR4 status, with a projection to advance to TR7 within 9 months through accelerated laboratory testing and material optimization protocols. Controlled environmental exposure trials will need to be conducted across marine, desert, Arctic, and high humidity conditions to validate performance integrity and durability metrics. Followed by limited battlefield integration with select platforms to gather real-world performance data against active sensing systems and to establish deployment protocols. Comprehensive integration across all relevant platforms is planned within 24 to 36 months, featuring customized formulations for specific operational environments and evolving threat profiles. Our team stands ready to conduct pilot demonstrations, provide technical briefings, and develop implementation plans tailored to your specific force structure and operational requirements. By leveraging this revolutionary technology, your legacy platforms can maintain battlefield relevance against next-generation threats at just a fraction of the cost of traditional modernization approaches. For more information about our nano-engineered stealth polymer solutions, contact Queensland Research Labs. Malcolm Lamont, email melamont@QldResearchLabs.com.